The topic for this talk is 60 object pose regression via supervised learning on point clouds. The task of 60 object pose estimation is to find the relative translation and rotation between a camera and a target object. If the camera is mounted on a robot, then this is an important subtask for robotic grasping. And if the camera is mounted on a mobile phone or a head-mount display, then this is an important subtask for augmented reality. Existing state-of-the-art methods that based on deep learning often use a convolutional neural network to extract deep features from RGB color information, and those features can be used to infer good 60 pose. In addition to color information, depth information can be treated as a fourth channel and used together with RGB information, also for feature extraction. And the extracted features can also be used to estimate good 60 pose. However, this kind of approach has two constraints. First, in order to process depth information with CompNet, the depths need to be a 2D structured matrix format. And if the depth is in unorganized structures such as a point cloud segment, it cannot be processed with CompNets. Another thing is that the color information is not always available if you use range sensors such as LiDAR, and in this case, only depth information is available. So in this work, we investigate whether we can achieve state-of-the-art performance when inferring 60 object pose from depth information. The depth information is represented by point clouds, and we do it in a deep learning-based framework. And to answer this question, we look into two aspects. The first is that since rotation and translation have mathematically very different metrics, as in radian and meter, whether they should be estimated with separate networks or not. The second is that a rotation can be represented by many forms, such as rotation matrix, Euler angles, and so on, and what would be a suitable rotation representation in a supervised learning framework. By studying those questions, we propose a framework called Cloud Pose. We start with two input images, a depth image and its corresponding semantic segmentation. A point cloud segment can be obtained as well as its object class label. We use farthest point sampling to get a downsampled version of the segment and feed it into two separate networks for regressing rotation and translation. The rotation and translation are further refined with geometry-based optimization to get the final 60 pose. Overall, it is a very simple structure system. Now let's take a closer look at the pose inference part. For the pose inference, the input is a point cloud segment with n points, and each point has its XYZ coordinate. Its class information is in one-hot encoding format, and K represents the total number of object classes. For each point, the XYZ coordinate is concatenated with a class vector, and for one branch, we calculate the coordinate mean and normalize its XYZ coordinates. The concatenated information is fed into two separate networks, and one network outputs the rotation in axis angle format, and the other one outputs the translation residue. The full translation is then obtained by adding back the coordinate mean. BaseNet is adapted from PointNet. PointNet is a deep learning structure that can be used to extract deep features from a set of unorganized points. And it does it By processing each input individually with a series of multi-layer perceptrons and extract 1,024-dimension features for each point. A global feature can then be obtained by max pooling, and then this global feature can be used for post-regression. In terms of rotation representation, we use axis angle format as a regressing target. An axis angle can be a three-dimensional vector, and it can be interpreted as a rotation of theta around the unit vector of E. One advantage of it is that it is constraint-free, so that the network output can be directly treated as a valid rotation. Unlike, for example, a quaternion representation is required to have a unit norm, and this would restrict the range of valid output for a network. And this could potentially make the learning task more difficult. We use geodesic distance as a loss function for rotation, and given the estimated and ground truth rotation in axis angle format, we calculate the corresponding rotation matrix and calculate the geodesic distance between them two. Translation loss is the L2 norm, and the total loss is a weighted sum of them two. In terms of geometry-based optimization, we use iterative closest point to refine the network output and get the final 60 poles. Now we know the network structure and the system details, it's time to check whether the resulting 60 poles can reach state-of-the-art performance. For evaluation, we use a YCP video dataset. It has 21 objects, more than 130,000 frames, and in total 92 video sequences. And we compare our method with Poisson and dense fusion. Here's a summary of performance on the YCP video dataset. The middle two columns are data modalities that were used during the post-inference stage, and the last two columns are performance accuracy according to ADD and ADDS scores. As we can see from the table, although only use depth information during the post-inference stage, our method still achieves very competitive results. Here are more quantitative results. We show the ground truth segment, the segment we use during test time, the ground truth pose, and the performance of the three methods. The pose performance are presented by overlaying the object model on the image from the predicted pose. As we can see that our method shows very stable pose estimation throughout the frames. More details and ablation studies can be found in the paper. To conclude this work, we answer the three questions that we posed at the beginning of the talk. First of all, it is possible to achieve state-of-the-art performance when inferring 60 object pose with depth information. And as the ablation study shows, we should estimate rotation and translation with separate networks. And finally, in a supervised learning framework, axis angle is a suitable representation for rotation. Source code is available on Git, and thank you for watching.